So we'll start with a couple of examples of single array detectors. So the first one we'll talk about is a photomultiplier tube. I've had the chance to use these type of detectors when I was a postdoc at Emory University. I was working on UV invisible spectroscopy using lasers there. And PMTs are great because they're very sensitive. They're single sensor detectors and they work in the visible and UV range. And so what they look something like this picture over here. So this is a picture of a PMT. And the way they work is they basically use the photoelectric effect that Einstein described. So once a photon comes in and hits a piece of metal, it generates an electron. And that's the photoelectric effect, is that once you get past, for metals, once you get past a certain frequency of light, electrons will be generated, they'll be ejected off the surface of the metal. And this has to do with the fact that you're ionizing the metal using the light coming in. And so when that electron is ejected from what's known as the photocathode is slightly negatively charged. And so the electron wants to leave because it's also negatively charged. So the electron leaves and goes to something that's slightly more positively charged, which is known as a dynode. And so in our figure down here, the dynode is represented by these curved lines here. So we have dynode number 1 here, 2 here. We see we have a chain of dynodes. There are lots of them. And there's a reason for this, is that when the electron from our photoelectric material, our cathode here, goes to the dynode that's slightly more positively charged, so the electron leaves the negatively charged cathode and goes towards the more positively charged dynode, when the electron hits, the dynode is made of a material such that when it's struck by an electron, it produces multiple electrons every time it's hit by an electron. So if we start with, say, just 1 electron here from our photon that hits, maybe we get 3 or 4 electrons from this dynode. And if we take 3 or 4 electrons and each of them produces 3 or 4 electrons, we get a cascade where these electrons keep multiplying and getting larger and larger. To relate it to a real-world relevant example here, this is like if you have a very high transmissibility for infectious disease like COVID-19. It only takes one case, will soon become thousands or tens of thousands or millions, as you keep doing this. It's a similar idea here, but for a much better cause than getting people sick. So we have, for example, in this one, there are 9 dynodes. And so for every 1 electron that's made from a photon, we get about 1 million electrons by the end of this chain of 9 dynodes. And so what makes this useful is that from a very small amount of light, we can get a very large signal that's easy to measure. And so it doesn't take, PMTs are very sensitive to even small amounts of light, which is what makes them still very useful, even though you can't really make a PMT array just because of the nature of the way they work. So that is one of the most common detectors used throughout the UV invisible because of its very high sensitivity to even to very small amounts of light. Now, if we move into the infrared range, most IR detectors are single sensor detectors. It is possible to make array detectors in the infrared, but they're very expensive and not very common, though they are becoming more common. And if you've seen any infrared cameras before, those rely on array detectors of infrared. But the idea is that these infrared detectors, these are what I'm most personally familiar with, use semiconductor materials with a band gap that roughly matches infrared wavelengths. And so when a photon hits that semiconductor material, there's more details to it than this, but it's not particularly relevant for our class here. It generates electrons, an electron hole pair, as you have a p-n junction. If that means anything to you, great. If not, don't worry about it. You're not going to be tested on it. And so it generates an electrical signal that we can measure. That's the long and short of it. So for infrared detectors, there are a couple of really commonly used materials. So those are MCT detectors, which are mercury cadmium telluride detectors, and InGaAs, or indium gallium arsenide. They work for slightly different wavelength ranges. I'm more familiar with MCT detectors because they work further into the mid-infrared range of infrared spectrum, whereas InGaAs is more near-infrared. But the details don't particularly matter here. Now, these detectors are often cooled to liquid nitrogen temperatures. And this is becoming less common, but it's still done. So these detectors, most of this detector here, this is an MCT detector, all this up here is just for holding liquid nitrogen. The actual detector itself is just this little circle right here. And so the rest of it is just electronics and keeping the detector cool. And so more recently, it's become more common. Instead of liquid nitrogen, you can get the performance of these has improved with technology. And so you can actually cool these with a thermoelectric cooler, so with electrical energy. And so you can get a much smaller detector and one that doesn't require liquid nitrogen to operate. And so this is an example of a more modern MCT detector and modern here means like within the last 5 years. So this is kind of an evolving field, and which is true for all of these sorts of detectors. The technology is constantly getting better and cheaper, which is one of the great things. And again, array detectors are not very common in the infrared because they're very expensive, but that is becoming less true as costs continue to come down on some of these types of detectors.